Now we're going to talk about a couple more different types of classification algorithms. So we're going to talk about 5 more classification algorithms that can be used in various different scenarios where maybe logistic regression is more difficult or more inefficient in its implementation. Okay, so really quickly, we're just going to run through a review of what classification is with our wine data set. So given all of our inputs, we're going to attempt to make predictions about what output category we can get. Okay, and the algorithms are named classification because each output category is known as a class. Okay, so categorical output labels are named as classes. So given our 11 total features in this case, as you can see on the left, same data set. Yeah, again, that's a lot of features. And so we this is actually considered, once again, a relatively small data set, but we kind of need to use something more than just linear logistic polynomial regression. And even more so, as we get into maybe 20 features or 30 features or like 100 features, you need to use more complex data sets. So let's start with our first new classification model, the decision tree. So decision trees, to understand this model, maybe it's easier to kind of take a look at an example. So let's say you want to buy a new pair of shoes, right? So let's say you have this pair of shoes. Does anyone particularly like them? Just curious. They're kind of yeah. I don't like them either. But let's say you want to buy some arbitrary particular pair of shoes, right? So you have to know its price. If it's like a $4,000 like Yeezy special collaboration, you probably wouldn't buy it. You have to know, maybe it's comfort. If it's comfortable, if it's rock hard, you probably wouldn't want to wear it. And you have to know if it's fashionable, because as everyone knows, wearing nice sneakers makes you look good, and that's always a plus, right? So maybe we can represent our decision boundary, but as something like this. So you can see if it's relatively comfortable and if it's relatively fashionable, then more likely than not we'll buy it. We can see that there's this kind of threshold in the middle where there's an area where you would buy it, there's an area where you wouldn't buy it, and then it's very clearly separated. And just as clearly, you can see that a linear model doesn't work very well at all. Even if you use this linear model as like a threshold, what if a shoe lands, for example, here? Or like what if it's in the middle section there, right? I didn't mean to hit that button. Our linear model might say yes if it's here, but we actually don't want to buy the shoe because it's still in the red region. Okay, so what do? We can think of this classification in terms of a flow chart, so to speak. And it's actually kind of similar to how humans would make decisions, right? So firstly, obviously you have to ask, can I afford it? Because if you can't afford it, there's no way you can buy it. And then if you can't afford it, is it comfortable? And maybe you prioritize comfort over fashion, right? So if it's comfortable, then you automatically say, yes, I'm gonna buy that because I need comfortable shoes. And if it's not, well, beauty is pain, so maybe you buy it anyway, if it's fashionable. And obviously, if it's neither comfortable nor fashionable, there's no reason for you to buy it. So unless, you're at Walmart and your selection is like Skechers, black Skechers, and like another pair of Skechers, you wouldn't buy it, right? So you can see, for example, if it was comfortable but not fashionable, you would go, can I afford it? Yes. Is it comfortable? Yes. And then you just buy it. You don't need to consider the fashion. Okay? Does that make sense for everyone? Okay, good. If we want to turn this into a more perhaps concrete or easy to evaluate algorithm for a computer, we can set some more concrete questions. Okay, so these here. So is the price less than or equal to $100? Is the comfort objectively greater than or equal to 8? And is the fashion objectively greater than or equal to 8? And we can ignore the fact that neither comfort nor fashion are objective, but for now we'll consider them to be objective, okay? So this gives us a relatively easy to explain and repeatable graph of predictions, but it also seems a little bit, hard-coded, right? Yes, thank you, KCD guy. So how do we make a computer kind of generate these trees based off of a huge data set that we give it. So instead of us generating the questions, how do we make the computer generate the questions, right? And that's kind of the central principle behind decision trees. Okay, so for example, let's take a look at this little data sample. Okay, so in particular, let's focus on this column, which says whether or not they were purchased. Okay, so this question here has two possible answers, obviously. Yes, it was purchased, or no, it wasn't purchased. And so you can think of a question as splitting a group of samples into the yes group and the no group. Okay, so let's look at a couple of possible splittings. For each of the following examples, okay, we're going to do the cheer boo thing again. You guys have just taken a break, you've socialized, you've worked in your lab, so, I want some energy, okay? So let's go ahead and do it. Ready? So this is the first split. How's that? Herd mentality. Okay, fine. This one? Okay. So actually the correct answer is no one should have said anything. So because we haven't defined what a good split is and what a bad split is. So thank you, brave souls that started the booing. You're wrong. I'm sorry. Okay. Or maybe you're not wrong. We'll see. We need to introduce a metric for this, right? So I'm going to tell you, as the creator of this lecture, that when we ask, okay, so let's ask which one is better, right? So I'm going to say the left one is better because it's a group, we have a group that is all no, okay? Whereas this group is mostly no. It's like 75% no, okay? And so now we can keep in mind that a good split, so to speak, means that there's one very homogeneous group and there's one potentially less homogeneous group, okay? So our goal is homogeneity. And computers evaluate this concept of homogeneity through an algorithm known as the Gini impurity, okay? So let's take a look at these two splits vertically. When a group becomes more homogeneous, okay, its Gini impurity will decrease. So up here, this quarter, this group has a Gini impurity of 0 because it's completely pure or homogeneous, okay? And so we can look at the Gini impurity scores for these 4 groups, and we can see that as a group becomes more homogeneous, like I just mentioned, the Gini impurity will decrease, right? So this one's majority homogeneous. This one is homogeneous, actually. This one is 75% homogeneous. This one is 67% homogeneous, and this one's like 50% homogeneous, right? So as a group becomes more homogeneous, its Gini impurity decreases. Okay, and then perfect groups are obviously, they have a 0 impurity. So this is the equation for the Gini impurity. It's another weird, complicated, notational equation. And then we'll examine that in a little bit. But we can see that to calculate the Gini impurity for a single split or a single way to split, you're always going to evaluate every single possible class. Okay, and that is an important thing. That's an important concept to remember, because as we delve deeper into this, it's going to become a little bit more confusing if you don't remember that. Okay, so make sure you remember the algorithm that's done inside is done for every single class, and that's how we evaluate the impurity. Okay, so when we calculate the Gini impurity, we want to loop through all these possible classes, right? And then find the product of the proportion of that class that we're interested in, and then the proportion of the class that isn't in that group. So if we had yeses and nos, we would say the proportion of nos times the proportion of yeses. Okay, and then we would go back and then we would say the proportion of yeses times the proportion of nos. And then we would add those two together. Okay, so armed with this more, specific metric, we can kind of look at our splits in a better and more objective manner. Okay, so let's go one more time. Okay, I'm going to give you the Gini impurity scores, and this time you should be able to cheer and boo very, very accurately. Okay, so here, okay, how's the first group? The top half only. Okay, good. And the bottom half? Yeah, exactly. Okay, 50%, 0.5, and total, the total is 1/2. Okay, And then similar concept. So what if we move the no and the yes up? 0.38. How do we think that is? Not bad. And then 0.5, once again, is also kind of not bad. But in sum, there's 0.88. Okay, so that's significantly higher than this one, which was 0.5. Okay. To be honest, I'm surprised that actually any of you said or cheered or whatever, because none of the Gini impurities, neither of those were 0. They were both like, so they were 0.5 and 0.88, right? But not very close to 0. Okay. So once again, as the creator of the lecture, I'm going to tell you that we can do better. Okay, we can actually achieve an impurity of 0. Okay, I'm not going to tell you how, but we can do it. Does anyone have any ideas for how we can do it? Or maybe do you want to brainstorm in your in groups before you do it? I will tell you that this requires some thinking outside of the box, okay? So there's not any rules. You just have to make the Gini impurity 0. That's your goal. Does anyone want to? Does anyone want to say anything? Please.
Just make each thing its own independent tree. So you have 6 different options.
6 different options.
Or 6 different trees with 1 option. If that makes sense.
Do you need to split everything into 6 different options?
You don't need to, but it'll make the purity 0.
Can you do so without making everything 6 different options?
Probably.
How would we do that?
You combine the ones that would be no's with ones that would be yeses.
What do you mean by combining?
So like at the top you have the no's. You just move that last node to the top.
Yeah, so you could sort your data set, yes, but that might present some problems in terms of like creating the test and training set and stuff like that. So let's assume that we have a randomized data set. How would you do it then? XKCD guy is here to help you guys though. How about that? The answer, of course, is just to split again. So yes, you are absolutely on the right track, right? You can split however many times you need to, okay? But the emphasis is also that you can split how many ever times you need to. So I wouldn't need to split all of the first 3 no's into 3 separate trees. I could just say, okay, the first 3 no's are 1 split. The next yes is 1 split, and then the no, and then the yes, right? So always you just, if you see a problem, just add in another split. Okay. And that is the basic process and the overall method we use, in fact, to generate these decision trees. Okay. We make a split, we calculate the Gini impurity, and then select a split that results in the lowest Gini impurity sum, which is usually 0. And then for everything else, just split it again. Okay, and you repeat it as much as you need to. Yes, please.
You have too many splits. Do you ever like get close to the line of overfitting?
With too many splits, do you overfit?
Yeah.
Yes. So, in some sense, it can. More likely is that you'll just ask a lot of unnecessary questions. So, like, is the comfort greater than or equal to 6? Is the comfort greater than or equal to 7? Is the comfort greater than or equal to 7.5? Is the comfort, you get the idea, right? So the way we adjust how many splits we make or how many times we go through this is with something called a hyperparameter. And the idea of hyperparameters is very prevalent in AI development. And essentially what a hyperparameter does is it's a number or a parameter that we use to control the parameters of the algorithm or the weights of the algorithm. And so in that sense, you control this hyperparameter in order to eliminate, that problem that you just described of like overfitting or like asking too many questions. Does that make sense?
So would you want to check the number of splits on the test data and not the training data? Cause you
you
wanna
can,
lower the Gini score of the test.
so the way you control the hyperparameter is, yeah, so you would test the algorithm that you built, I guess, on your test data. And then you could adjust like the training, like how many times you run through the training, that hyperparameter. And then you can test it on the test data multiple times and see which is better.
So usually you select like the separate test data from your actual test data. So if you try to tune hyperparameters using the test data, then it's more like cheating. It's like giving the student too many heads. Yeah, so usually people use something called
Level,
old validation, cross validation, they use like the validation data set. So, and you can think of it as a practice exam where you're given the key. So you try different studying methods and then until you perform very well on the practice test, on the practice exam, and then the actual exam, you're not allowed to do any tuning. So you just have to take it and not miss it. Yeah. And one example of a hyperparameter which you guys use is the max filter. So that's a hyperparameter, something that you feed to the model.
Thank you very much, Professor. So now that we've gone through decision trees, okay, I have a bit of a question. Okay, so what if we did multiple different decision trees, okay, and we had them predict at random? Would the results, would all of these results be different? Think about that. Okay, ready? I'm gonna count down from 5, and then people who say yes, okay, you vote with I. The people who say no vote with nay. There's a reason for this, but we'll get into that. Okay, ready? 5, 4, 3, 2, 1.
Yeah.
Okay, so more nays than ayes. Okay, so technically, actually, yes, this is kind of I wouldn't call it an indeterminate algorithm, but you can create different decision trees from the same data set. And the way you do that is maybe by shuffling the data, maybe by asking a different starting question, but you can do that in a lot of different ways. However, the important part is having all of these, having all of these voters of decision trees allows us to get a more, I guess, not generalized, but a more robust prediction. Okay, and so the reason I had you all vote with aye and nay is that you've just reenacted the very prestigious Council of Trees. Okay, and this is the idea behind our second classifier called the random forest. Okay, so the random forest is essentially making a lot of different decision trees on different portions of the data, on different with different questions, stuff like that. And then for a new sample, you run everything, and then you combine the votes and you take the majority that the random forest, the Council of Trees, as it were, voted for. Okay, so those two classifiers are very closely intertwined, and essentially they're built on the same premise of that kind of flowchart that we saw at the beginning. Okay, now the idea of splitting has been made so far relatively analytically and numerically, right? But we can also talk about this graphically, right? So what if we looked at, a graph of our data instead? So let's take a closer look at how our splits might be represented graphically. Here, our bought shoes, by the way, are green, and then our rejected shoes are red. So, for example, here's some splits that we might do. So something like this, right? But these lines are very reminiscent of the function that we had at the very beginning. Namely, what if we have a shoe that's like, here that we're trying to predict, right? So the lines kind of say no. The lines put that point into the red region. But if we overlay with our initial kind of buying parameters, then we can see that we would actually buy the shoe. So how can we kind of rectify this issue, right? So our model tells us to reject, but it's actually an accept. Okay, so how do we rectify that issue? Well, we need to use a more complex split. Okay, so like a slanted line or a curved line. And we're going to do this with our next classification model, which is called a support vector machine, or an SVM. Okay, so support vector machines down, bottom line. So the way support vector machines work is that their goal is to create some sort of line or curve that is the most splitting, if that makes sense. So it's as far as possible from every single point, and it's maximizing that minimum distance between the line and the point. Okay, so it'll end up somewhere around there, more or less. You can see if you move it down too far, it's going to be really close to all the red ones. And if you move it up too far, it's going to be really close to the green ones. Before we move on, I'd like to acknowledge the fact that we have plenty of pizza here. So it is like 4:30.
It's 4:25.
4:25. It's a little bit maybe early for dinner, but if you guys feel like grabbing a piece of pizza, please just stand up and, you know.
Give us a minute to put it,
Enjoy it.
it's around the tables and just take them.
Oh, that works, yeah. But in the meantime, we can continue with SVMs. As much as they're not as engaging as pizza, we can take, right? So you can see that this line has a very fine margin of error, especially with this specific data set. Because if you move it a tiny bit down, it's gonna hit the red points. And if you move it a tiny bit up, it's gonna hit the green points, okay? If we zoom in, we can see this issue is even more apparent, okay? So this is magnified, I think somewhere around like, I would say maybe 10 times or so. And with these points in particular, okay, those two are our closest points in the samples. You can see that if you move the line even a tiny bit down, it's immediately going to hit that reject point. And if you move the line a tiny bit up, it's going to immediately hit that accept point. So it's a really, really fine margin of error, okay? So the split we want is to have the closest points as far away as possible. Okay, so can we do better than, something like this, like a straight line? Thank you so much. Really, okay, actually, this is important, okay? So aside from the concept of like straight lines, okay, distance, whatever, does everyone like pineapple on pizza?
No.
Yeah.
Okay, I'm sorry to, thank you so much. I'm sorry to distract you from your pizza, but can everyone stand up really quickly? Okay, stand up and then come to the center of the room. Where I am, okay? Go that way to that side of the room. If you're actually just make it a scale, okay? So this is completely neutral. And the more you go that way, the more you like pineapple on pizza. The more you go that way, the more you hate pineapple on pizza, okay? I'm sorry that there's no door in that wall, so you can't exit. But figure out the scale. I'll stand at neutral for now, but I'm not neutral, okay?
Pineapple and jalapeno.
All right. For reference,
Now turn this way.
I'm not gonna vote.
Oh my god, oh my god.
That's not right, Jack's computer. We'll never come
All right, so for reference, I'm over there, but I'm gonna act as something else, okay? So assuming maybe, let's assume you were slightly on this side, okay? Just for, I know you're neutral, okay? If I stand here, I'm being that splitting line right now, okay? And if you guys were like, let's say there were more dimensions. So let's say you guys were in like several, like spread out either way. Okay? Now, even though the line is still horizontal, more or less, okay? Now, my goal as the splitting line, as a support vector machine, is to maximize my distance between what's your name? Between V, Henry, between everyone who's close to me, okay? That's how support vector machines work. Thank you, by the way, for everyone who voted on this side. Sorry for everyone. Okay, you can go back and sit down. Okay, so if I were more flexible, which I'm really not, especially in, this kind of right? So if I were more flexible, I could maybe become something like this, okay, this curved line. And that maximizes the distance between the successful or like the accept points and the reject points even more, okay? And so that's essentially that's the concept of a support vector machine, is to make the distance between, make the smallest distance, I guess, between this splitting line and the points as big as possible, okay? Support vector machines, that's what helps us make this split as good as possible. Okay, So support vector machines, yeah, they're classifiers that divide data by class. And they want to create this margin as wide as possible. And importantly, they can use nonlinear functions, okay? So when we implement support vector machines, there are a lot of different what are called kernels that can be used to implement these machines. And what these different kernels are essentially that there are different types of functions that are used in order to build different like types of splitting lines. So sometimes a linear line, if that makes sense, works the best. Or sometimes some other function works the best. But these SVMs are very powerful in that they can establish many, many different types of splitting lines or margins, okay? And we can see even with this relatively simple SVM, it's pretty much almost an exact match to what our original decision threshold was, okay? So does anyone have any questions on either support vector machines or why I like pineapple pizza? Yes, so sorry. The kernel of an SVM is essentially the type of function that it uses. So like linear or Gaussian, I think is one, or like some other type of function, right? And all of the different options are generally the documentation. It varies by implementation, but it's the type of function or the type of curve that is used in order to generate this split. That makes sense. Right, great. All right. So let's say you got this email. Okay. And I'm sorry if you did. You'll see why. Does anyone want to volunteer to read this email to us? Or are you all to? Yes, please. Okay.
Hi, good day to you. I am Stephen, a U.S. soldier currently carrying out my duty in Syria. I have a proposal for you. I and some of my colleagues recovered a huge amount of money here last 2 weeks during an operation. We just shared the money some days ago, and I want to move mine to a safe place. That's why I'm contacting you through this mail, because this is the only means of communication I have here. I came across your email when I was searching for a random person online, but it's not gonna happen. I'm willing to offer you 40% of the total money, which is 17.8 million USD, if you are willing to do the deal with me. And I also want you to know that this is very legit. Here's my personal email address, stephen@yahoo.com. You can reply to me here if you are willing to do this deal with me, and I will advise you ahead. I will advise you ahead on how I will send the fund out to you. You are to ignore this mail if you are not interested. I will wait for your response. Best regards.
Thank you very much. All right. So
You're a great random person.
So before we go into how we can build an AI spam classifier, let's build a human spam classifier, okay? So very simple. Is this spam or not? Yes. Okay, great. Great job. Our human spam classifier is 1 for 1. Okay. So very obviously, it's very easy to tell that this is very spam. Okay. So how about this one? Who wants to read this one? Maybe I can eat it, given that you're all eating pizza. Internal memo, 146 Hagley Road, Birmingham, whatever address. From the desk of Mr. Jerry Smith, very generic. Date, 13th of January, 2014. Attention, sir or madam, I seize this opportunity to extend my unalloyed compliments of the new season to you and your family, hoping that this year will bring more joy, happiness, and prosperity into your household. I'm certain that by the time you read this letter, I might have already gone back to my country, United Kingdom. I visited South Africa during the New Year period, and during my stay, I used the opportunity to send you this letter, believing that it will reach you in good state. Let me remind you, I don't think the UK has to date. I could be wrong about that, but you never know. And then this email goes on to talk about, I think it was a family member or relative dying of some disease or another, a very large lucrative sum of money, and basically the contents are similar to the last email from there on. Okay. So evidently, actually, human spam classifiers, this spam. please. Yes, okay, great. 2 for 2. So evidently, we can tell that both of these emails are spam, right? So how can we tell that? Would anyone like to oblige the question? How can we tell that? Please. Bad grammar, terrible grammar. Yes.
Large sums of money.
Large sums of money, right? So language such as, large sums of money, or like, I hope this email finds you in good state, or like unalloyed compliments, or 100,000, yeah, large sums of money, or like relative dying of cancer. All of these, this is not something you send an email about. I personally would call the person. That's just me. I could be alone just like I am with pineapple pizza. Actually, I'm not alone. But anyway, Mr. Jerry Smith is A, very patriotic, B, very philanthropic, and C, a spammer or scammer, right? And so both of these things very clearly to us are determinant of spam, right? So in other words, we can write this, mathematically. Perhaps if we have this, then we get this, or something like this, right? So we get A if we have B, or we get spam if we have large sums of money, or terrible grammar, or something like that, right? So yeah, we get spam if we have Nigerian prince. I don't know. Sorry, Prince Kunle. Okay. I'm sorry, but it was the most commonly it was the most common result that popped up on search. I didn't make this slideshow. Please take it up with the creators. But anyway, we can use this kind of conditional probability of spam given whatever conditions we've just discussed to tell us if these conditions are good indicators of a spam email. So if this conditional probability is high, then we have probably spam. So if this conditional probability is low, then it's probably not spam, right? That makes sense. So in other words, conditional probabilities can be used as a classifier, okay? So the formula will become something like this. It's called the Bayes equation, okay? So we take everything on the right side, which is these things, and we turn it into our desired conditional, which is we get spam if this thing appears, okay? And so we multiply the percent of the data set that is spam by the percent of spam that has whatever condition, and then divide it by the amount of condition in the whole data set, okay? And if we want to include more conditions, we just multiply, okay? However, this is called the naive Bayes classifier for a particular reason, and that's because this multiplication assumes something called independent probabilities, okay? So how many people have heard of independent probabilities? Yes? Okay, a couple people, okay? Just to be a bit more specific, independent classifiers are naive because they assume that two conditions aren't related when perhaps they could be. So let's look at an example. So for example, the probability of sun versus rain, right? Now, the probability of sun, say, and rain on January 1st might not be necessarily dependent. Obviously they are, but the probability of rain on both days might be. So let's say P rain on January 1st is 50%, as is P rain on January 2nd, okay? However, P rain on both is not necessarily P rain of the first one times P rain of the second one, okay? As you can see, if you've lived in New England for a long time, weather does not work like that. It's not predictable, okay? So more specifically for us, the 2 days depend on each other. So you can't really just independently multiply them, right? So you might say the first one is 45%, whereas the second one, the result you get is 25%, okay? So really multiplying it like this doesn't work. And that's why we consider this classifier to be naive, because everything is assuming that, the probability that you have A is independent from the probability that you have B. Okay, so even if you have A and B, it's not considering that there might be a relationship between the two. So that's why we call it naive. Okay, does everyone understand the naive Bayes classifier and why we consider it to be naive? Great. So for our final classifier, it can be just kind of epitomized by the following question. Okay, so let's say you have this apple here. Would you buy it or would you not buy it? Right? That's essentially the whole question. I don't think, it's hard to determine whether or not you would buy this apple because it's a stock image and it's not very representative of an apple, but that's our question here. So let's say you've bought those 4 apples, which are really just resized images of the original apple. And let's say you didn't buy those other apples, which are again resized images of the original. Okay. Does anyone notice any particular trend between the apples? Like which ones do you buy? Which ones do you reject? Yes, go ahead, shout it out.
You bought the smaller one?
Yes, you tend to buy smaller apples and not larger apples, right? Maybe you have a small mouth, I don't know. So if we put these apples on a scale like this, okay, we can take our apple to buy and evaluate its nearest neighbors. Okay, so let's say it's closest to those couple apples. Obviously, we don't want to buy that apple, right? And this is the premise of our last classifier, k nearest neighbors. Okay, so we can do k nearest neighbors with 1 dimension as we did there, so just the size. And we can also do it with, something that's 2-dimensional. So for example, let's say this basketball is determined by its radius and its bounciness. Okay, I don't play basketball, I play volleyball, so I don't know if that, makes for a good basketball, but let's just go with it, right? So let's say this basketball that we're about to buy falls somewhere there, right? So if we take, say, the 5 nearest neighbors, then we can see that we will buy this basketball because the 5 nearest neighbors are 3 buys and 2 don't buys. Okay, and buy outweighs don't buy. Now, the number of parameters, so k equals 5, whatever k is, that's another hyperparameter for us to consider. Okay, so if we were to take k equals 7, we would actually say don't buy because the next 2 nearest neighbors are actually both don't buys. So this is an example of a point where it's very important, I would say, to make sure you select the correct hyperparameter and make sure you figure out, how many neighbors do you want to take, because they can actually affect your prediction. Okay, and as you can see here, it does affect your prediction. So that was a lot. That was 5 classifiers and some pizza and some pineapple voting.